Okay, in this video, we are going to learn about properties of logarithms. We already know that logarithms are exponents. They're a way to take an exponent, which is superscript, which means it's above where the coefficient is, and rewrite it as a coefficient. In other words, if we have a base to an exponent equals the argument, we can rewrite it in logarithm form, which would be log of the base. The argument goes here, and then that's equal to the exponent. And now this superscript exponent is down here, written not as an exponent. It's at the same level as a coefficient. So we know this as far as the definition of a logarithm, but now we need to figure out how to use logarithms in order to rearrange equations that are more complicated than the ones we've done so far. And to do that, we need to review the rules of exponents. So let's do that. We're going to do rules of exponents and apply them to logarithms, since logarithms are exponents. So I have that written on the left-hand side already, but let's go through some actual examples so you know what I'm talking about. So rules of exponents. The first one written on the left-hand side is multiplication of bases. We add the exponent. I feel like everybody can do this. X squared times x cubed. That means we have the same base. We add the exponents. We're going to get x to the 5th power. So this is multiplication of the base. Our rule is to add the exponents. How do we apply that to logarithms? Well, if we see that the exponents are added, let's say we have log base 10, so I'm just going to leave that off. Log of x plus log of y. If we see addition, add exponents, these are logarithms, there's 2 of them, they're added, then we can go vice versa and combine them to say that this is log still base 10 of x times y. So addition and multiplication go together. The order is important. So we're talking about multiplication of the base here. This time we're talking about the addition of the arguments. It means that we can multiply the arguments together. Our second rule is going to be division. So if I say I have x squared divided by x to the 3rd power, then we know that the rule is if we have division of the base, that means we're going to subtract the exponents. And we don't always work this one out by this rule. We often cancel on the top and the bottom. We have one left on the bottom. But the rule says that we need to say keep the base, the top power minus the bottom power is x to the -1, which ends up being 1 over x is how we write it. But the subtraction here, that's the rule. So if we apply that to logarithms, we're going to say if we had log of x minus log of y, anything that has a minus like this is going to go in the bottom when we combine them. So we're going to write 1 log, combine them, we have x on the top and y on the bottom. So anything with a negative in front of the logarithm goes in the denominator. So as long as you're with me that logarithms are exponents, these exponent rules apply. One last one we're going to do, if we had x squared raised to the 3rd power, that means we have x squared 3 times of this, whatever this is, and that gives us x to the 6th power. The short way to know it, though, is if we raise power of a power, we keep the base and we multiply the exponents. So same rule is going to apply with logarithms. We're going to say that if we have log of x squared, then this is power of a power, and so we're going to multiply. And so what I like to do is draw my rainbow backwards. This is equivalent to 2 times the log of x. And we're going to work some math so you can see how this all works out. But these rules all go together because logarithms are exponents. So let's do some math and see how the simplification helps us. These kinds of problems where we use these properties are considered to be expansion or contraction of the expressions. So we're going to condense them or expand them. This particular set of questions is going to be expanding logarithms. So we have an argument with things multiplied out. Or things multiplied together. So 64 times x cubed times the square root of y, and the directions say use the properties of logarithms to expand the expression. So we're going to write them as separate logarithms using the rules that we learned just a minute ago. So because we have multiplication here, multiplication goes with addition. So when we separate these, we're going to write them as 3 separate expressions. We have 3 separate bases within our argument. So each one is going to get its own logarithm. They will all have base 4. So first I'm going to write log base 4 of 64, that's the base, plus, because multiplication and addition go together, log base 4 of x cubed plus log base 4 of the square root of y. Now I'm not done because the directions say expressions should be expanded as much as possible. So I need to go to each of these and see if I can rewrite them even further. 64 I'm going to write as log base 4 of 4 cubed plus log base 4 of x cubed plus log base 4 of y to the 1/2 power. Now I have an argument that has an exponent. So we're going to take that, and this is power of a power rule. So we're going to take this as multiplication. We're going to put this in the front as the new coefficient. So I've got 3 log base 4 of 4 plus, same thing here, 3 log base 4 of x plus, this one's a half, 1/2 log base 4 of y. There's one more simplification that I can do, and what I want to do is simplify right here. So log base 4 of 4 is equal to a number. So logarithms are exponents. What's the logarithm for just this one piece? What's the exponent that means base 4 here? What exponent makes 4 into 4? And that's going to be 1. It's again, and I've talked about this before, inverse operations. This is log base 4. This is an exponential with an exponent of 1, and these cancel each other out. And this ends up simplifying to simply 3. This is 3 times 1. The log 4 and the 4 cancel. We're left with 1. Or you can ask yourself the question, what's the exponent that makes 4 into 4? And that'll be 1. You could rewrite it. So over here, log base 4 of 4 equals x, and solve it. 4 to the x, 4 to the x equals 4. 4 to the x equals 4. And so x equals 1. So this whole thing simplifies to 1. So this one simplifies to 3 plus 3 log base 4 of x plus 1/2 log base 4 of y. So sometimes in simplifying them, expanding them, there are things that you can simplify that you'll want to go ahead and simplify. You could have done that here, but I wanted to show you that putting the 3 in the front gives you the same exact thing. So if you'd have noticed it here, this is a base 4 and this is a base 4, and so this whole thing simplifies to just 3, which is what happened here. So this is the expansion of this logarithm. For my second example, I'm using the natural log function. It works the same way. It's still a logarithm. It just has base e. So when I expand this, these are the same directions as before. I'm going to have, again, three bases, x, y, and z. So I'll have three separate natural log things written out. First, I want to rewrite this just so everybody can see that this is the same thing as xy squared over z to the fourth, all raised to the 1/3 power. And written like this, we know in exponent rules, this 1/3 gets applied to everything because there's no addition or subtraction here. So this is actually the same thing as the natural log of x to the 1/3 times y to the 2/3 over z to the 4/3. So my argument now has separate exponents. Now when I write it out separately, I'm going to say I have the natural log of everything that's multiplied gets a positive natural log in the front. So I'm going to have x and y as positive natural logs, and then I'm going to say subtract the one on the bottom. And you can write it in any order you want. I could start with the negative z if I wanted to, the negative natural log of z. But I'm going to do them as I see them in order. I'm going to do x first. This, being the exponent, is going to go in the front, the natural log of x, plus, so there's a positive there because this is a positive in the top. Then I have the natural log. I have 2/3 the natural log of y, and then I have subtract the natural log, and then I'm going to squeeze a 4/3 in there of z so that I have everything written out. In the book, they wrote theirs differently. They wrote from this, they said, actually from this scenario, so really from here, they said, what if I take the 1/3 right now? I consider this one unit. I take the 1/3 to the front. Then it would be 1/3 the natural log of xy squared over z to the fourth. And then from there, to separate them, we would have the natural log of x plus 2 the natural log of y minus 4 the natural log of z. So either one of these is correct. We would still get 1/3 natural log of x. And then we'd have 1/3 times 2 is 2/3 the natural log of y. 1/3 times -4 is -4/3 natural log of z. So they're both equivalent. Either answer is correct. For example 2. For example, this is written as times. This is scientific notation. Recall that log base, not written, means 10. So when you write that out, you want to consider that because there's obviously a base of 10 here. So to write this one out, we've got two terms that are going to be positive in the front. They're going to be added. This one will be subtracted. So we have log base 10 of 2.7 plus log base 10 of 10 to the fourth minus log base 10 of x to the -2. So this one's going to stay the same. This one, if you want to write in the 10 so you can see it, the log base 10 and the base 10 cancel. This simplifies to 4. This last term, when we move -2 to the front, we end up with a positive 2 log of x. So our final answer, completely simplified, is log of 2.7 plus 4 plus 2 log of x. If you're given access to a calculator, this is actually a number. You can plug this in the calculator. This, I don't know unless someone tells me what x is. So in the book's example, they said, okay, if you have a calculator, you can type this in, log of 2.7, and then come up with a simplified answer. So log of 2.7, so that's going to be 0.43136 plus 4 plus 2 log of x. So these two can be combined, 4.431 plus 2 log of x, rounding to 3 decimals, which they didn't tell us how to do. So this would be the exact answer, and this would be the rounded answer. So far with our rules, we've used Combined arguments can be separated based on exponent rules. So things that are multiplied are positive. There's an addition in between them. Things that are in the denominator are subtracted. And powers for those bases are multiplied, so they're put in the front. Okay, so now we're going to work those same rules in reverse. This time we have expanded logarithms that have the same base of 3, and we want to condense them into one logarithm. So we're going to use the properties that these are exponents, and if there's subtraction here, that means division, or we could consider it as an exponent. So let's look at that. We could take this one and simplify it. We need to move the 2 before we can do any sort of combination here. We need this to be just log base 3 without the 2 in the front. So first, right underneath it, I'm going to write log base 3 of x over 3 all squared. This 2 moves now to an exponent position, and it's squared. If we do the same thing with this one, we can change it to, we can say this is a -1 exponent. We can say change that to plus log base 3 of 1 over y to the -1. The reason we do that is because this is going to be a fraction, and if we divide by the fraction, we've got fraction rules to deal with. So simplify within, now we have log base 3 of x squared over 9 plus log base 3 of 1 over y to the -1 means move the y to the top, so this is just y. Now we can simply rewrite it. This plus changes into multiplication. We're going to combine the logs now at this point. All our simplification is done. We have log base 3 of x squared over 9 times y. You can leave it like that. You could put it, the book shows the answer as x squared y over 9 as the argument. Either one of those is perfectly fine. Example 5 is also condense. That means we're trying to write as one logarithm. One logarithm. So here we've got addition. This one's positive. It doesn't say positive, but now it does. Positive, positive, negative. So consider that as you look at the problem, things to consider. They all have natural log, which means they all have the same base. First, I want to simplify because this has a number in the front. I need to move it to an exponent. So I've got the natural log of x squared, which was ready to go, minus the natural log of y to the 1/2 plus the natural log of 2. So now when I rewrite it as one logarithm, the natural log of x squared is positive in the front, which means that it's positive. It's in the numerator in my condensed version. This one is going to be, because it's a negative, that means subtraction. That means it's going to go in the bottom for my logarithm, y to the 1/2. And then this one is positive, so it's going to go in the top. Normally we don't write it that way. We would write 2x squared and then y to the 1/2. Or you could certainly write that as the square root of y, because that's what that means. So it's totally up to you. At this stage in math, we all agree that the square root of y is the same as y to the 1/2. So either format is fine there. All right, so you have some practice problems that deal with the rules of exponents. Work on those, check your odds. We'll look at any evens together and then go over any questions that you have. You need to memorize the rules of exponents and think of them applying to logarithms as exponents. So these rules will feel unfamiliar until you get some practice with them, and when you finally are okay with logarithms being exponents, the rules will make that much more sense. We'll do some more examples tomorrow and look at change of base and other applications for logarithms. All right, thanks.